Alright guys, welcome back to Underground Science, and in this video we're going to be looking at the parts of an action potential graph and trying to become familiar with it, so when we actually talk about the physiology of what's happening inside a neuron and what's happening in an action potential graph, step-by-step process, we'll know what we'll be more familiar with and it'll be easier to understand. Alright, so let's do this. Okay, so I feel like in the last video when I talked about the graded potentials, I kind of rushed over the action potential graph part and I kind of made it confusing, I feel like. So let's just go over the basic parts of an action potential graph, right? So let's go and decode that part first. So let's go and draw our nice graph here. So remember, we have our time on the x-axis in milliseconds, and we have our membrane potential in our y-axis. So membrane potential is going to be in millivolts because we're talking about electricity here. And let me do a better job of writing this, not get too lazy. All right, membrane potential, membrane potential. All right, come on. There you go. All right, so that's good. So we have our time on our x-axis and membrane potential on our y-axis. All right, let's go and fill these arrows in. Okay, so what happens, remember in the last video we said that we have a resting membrane potential of a neuron. Okay, so there's always going to be a resting membrane potential of a neuron, and it may differ between the neurons, but if you take the general point of, or the general value, you'll see that the resting membrane potential of a neuron is about negative 70 millivolts. So what does that mean? If the neuron has a resting membrane potential or is in a resting membrane potential, it means it's not firing yet. Okay, there's no action potentials firing down the axon, or we don't have any graded potentials coming in enough to reach that threshold potential. Now you might see something called temporal summation and spatial summation. Okay, temporal summation is pretty much how many graded potentials add on to the height of each each summation. All right, so what I mean by that is here. So let's go and look at that. Okay, so let's see, let's draw in red. So let's say this is our resting membrane potential, right, at negative 70 millivolts. Let's go and draw let's say we have a negative 45 millivolt threshold potential. So our threshold potential is the least amount of millivolts, or the membrane potential a neuron has to reach in order to go our all or none phenomenon and fire up to positive 35 millivolts. All right, so let's say we have, remember in the previous video we said we have some graded potentials coming out our dendrites, right? But remember, as those graded potentials travel down and reach our axon hillock, by then, those graded potentials have decreased in strength and size. Okay, so it may have seemed like a very hard and strong excitatory signal on our dendrites, but by the time it reaches the axon hillock, it's not really that strong anymore. So let's say we have a short depolarization here, but we don't quite reach this negative 45 millivolts, right? But let's say we just don't have one excitatory signal, that we have many strong excitatory signals coming in. What can happen is those excitatory signals can sort of overlap each other, and they can keep on doing that until we reach the threshold potential, right? Let's say, bam, right there, reach the threshold potential, and right from there, then we're going to see our whole action potential, right? But in general, these groups right here, we see temporal summation and spatial summation here. Temporal summation being that it's increasing in amplitude, or it's increasing in height, right? So right here, we can see that our action potentials right here started off low and it kept on adding together, because we're talking about summation here. Temporal summation is when it adds together in terms of height. Subspatial summation is pretty much what it says. It's adding in terms of our width, or our wavelength, you can say. If these aren't sound waves or anything, but I'm just trying to say that we're talking about summation in terms of width here. Okay, so our length of our graded potentials are increasing in terms of time. All right, so we're having both temporal summation in terms of height and spatial summation in terms of width. All right. And this is going to add up because of many positive excitatory signals, okay, our graded potential at our dendrites. which is going to reach our axon hillock and add up until we hit that awesome threshold potential, and then our axon hillock's like, all right, bet, let's fire an action potential because we've reached our threshold potential. So then we immediately fire. So we go up, and then it reaches here, and we're just like, oh crap, here we go. Right, we fire an action potential, goes up to about, kind of went too above here, but this is going to be about positive 35 millivolts. And then we're going to go back down, right? You're going to see that we don't stop at negative 70, guys. We actually kind of dip below negative 70, and then we come back up slowly, and then we get ready to fire again. All right, and so this stage right here is called our hyperpolarization state. All right, so this is our hyperpolarization state because it's not depolarizing, it's not getting more positive, it's getting way more negative than it's supposed to be. And we're also going to talk about our refractory periods, all right, in our future videos. But for now, let's just say that this is our hyperpolarization state. All right, so this, let's go and label it since we're doing that right now. This whole part right here is our repolarization state. Repolarization pretty much means our membrane potential is getting negative again. Okay, so repolarization state. All right, and then this part, guys, right here, remember, is our depolarization state, because depolarization means our membrane potential of our neuron is getting more positive because we're firing that action potential, right? So this is going to be our depolarization state of our action potential curve. Okay, and again, about negative 45 millivolts is our threshold potential. That's the minimum amount of threshold our temporal summations and our spatial summation, our graded potentials have to reach in order for our action potential to fire and follow that all or none phenomenon. All right, so threshold potential, and this, guys, remember, negative 70 about millivolts is our resting membrane potential of our neuron. So when it's not firing, right, when our action potentials are not firing, is our resting membrane potential. All right, and when we go down to our hyperpolarization state, we can estimate that to be about negative 85 millivolts. All right, again, these can differ, maybe +5 or -5 millivolts in some textbooks and websites, but we're going to take the general value and go and say negative 85 millivolts. All right, so let me go and draw this arrow because it kind of looks like I'm pointing to the wrong thing here. This arrow is pointing to negative 70. However, let's go and change colors, and we're going to say the negative 85 is going to be our point at which the hyperpolarization state hits. Okay, so this is our, let me just go and draw the arrow right here. All right, so we can see the connection between our hyperpolarization state and negative 85 millivolts. All right, and we'll talk about our refractory periods in a future video, okay? But this is pretty much the basic labeling part, if you would say, of an action potential graph. And I feel like this would help us when we actually talk about what happens, like what each of these parts mean of an action potential actually inside a neuron. Because inside a neuron, we have some stuff going on, all right? Some cool stuff, like a bunch of sodium channels and potassium channels, sodium-potassium pumps, right? We have some potassium and chloride pumps, right? Calcium and sodium pumps, and way, like, a lot, okay? So hopefully we can squeeze that in our next future videos, and hopefully it'll be fun, all right? So I hope that I made sense to you guys in this video. I hope I wasn't too, like, boring or confusing. And so in the next video, and then in our future videos, we'll talk about more cool topics in the nervous system and the rest of physiology and bio and biochem, chem, and physics. So I hope you guys keep on coming back so we can keep on learning science together here at Underground Science. And I hope you guys already hit that notification bell so you know when I'm publishing my videos. And don't forget to like and subscribe, and see you guys later, and hope you guys stay safe.